Hey everyone, welcome back to the channel. In today's video, we're diving into one of the most frequently discussed topics in Python interviews, multithreading. Multithreading is all about running multiple threads of execution within a single process, which can be incredibly useful for speeding up IO-bound tasks like reading from files, making network requests, or handling multiple user inputs at the same time. We'll go through some practical examples to help you understand how multi-threading works, the challenges it presents, and how you can use it effectively in your code. Whether you're preparing for an interview or just want to deepen your knowledge, these examples will definitely give you a solid foundation. Definition: Multithreading in Python is a way to run multiple tasks at the same time within the same program. Think of it like multitasking, where different threads handle different parts of a process without slowing each other down. Threads are lightweight and share the same memory, so they're great for tasks like reading from files, handling network requests, or managing multiple user interactions, where the program might otherwise have to wait around for something to finish. Python makes it easy to work with threads using the threading module, which helps you run tasks in the background while the main program continues running. However, there's a catch: Python has something called the global interpreter lock-kill, which means that even with multiple threads, only one can execute Python at a time. This makes multi-threading less useful for tasks that require a lot of CPU power. But for tasks that spend most of the time waiting for input or output, like reading from a file or making a network request, multithreading is still very effective. Key benefits: Multithreading offers several key benefits that make it an efficient approach for handling multiple tasks concurrently within the same process. One of the primary advantages is concurrency, allowing multiple tasks to run simultaneously, which is particularly useful for improving performance when tasks can be executed in parallel. Since threads share the same memory space, shared memory becomes an advantage, as data can be exchanged easily between threads without the need for complex inter-process communication mechanisms. Multithreading is especially effective for IO-bound tasks such as file operations or network requests, where the program spends most of its time waiting for external input-output operations to complete. By using threads, these waiting periods can be managed more efficiently, allowing other tasks to proceed without delay. Additionally, threads are lightweight, meaning they consume less memory and take less time to create and terminate compared to processes, making them a more resource-efficient option when you need to handle multiple operations concurrently. Python's threading module provides Python's threading module offers several powerful tools for creating and managing threads, enabling efficient concurrent execution of tasks. The most basic feature is the thread class, which allows you to create and manage individual threads. To ensure proper synchronization between threads, especially when they access shared resources, the module provides a lock, which prevents race conditions by allowing only one thread to access a resource at a time. In addition to locks, the threading module includes other synchronization primitives such as event, condition, and semaphore. These tools help threads communicate and coordinate their activities, ensuring proper execution flow in multi-thread execution. For higher level thread management, the thread pool executor is available. This feature allows you to manage a pool of worker threads that execute tasks concurrently, making it easier to handle multiple tasks without manually creating and managing threads. Now that we've covered the basics of multithreading and how Python's threading module works, let's dive into some practical examples. We'll explore how to create and manage threads, handle shared resources using locks, and see how these tools work in real-world scenarios. So let's jump into the code and see multithreading in action. 1. Basic thread creation. Question: Write a Python program that creates two threads that print numbers from 1 to 5. In this example, we demonstrate how to create and run multiple threads in Python using the threading module. The goal is to execute a function concurrently in two separate threads. The function print underscore numbers prints the numbers from 1 to 5 with a 1 second delay between each number to simulate a task that takes time, such as processing or network communication. Using threads allows both tasks to run simultaneously rather than sequentially, making the execution more efficient in scenarios involving IO-bound tasks or tasks that can be run in parallel. We create two threads, thread 1 and thread 2, using the threading.thread constructor. The target print underscore numbers argument specifies that both threads will execute the print underscore numbers function concurrently. When we call thread 1.start and thread 2.start, each thread is executing its copy of print underscore numbers running in parallel. Since both threads are printing numbers concurrently, the output will interleave numbers from both threads, demonstrating the concurrent execution. To ensure that the main program waits for both threads to complete before proceeding, we use the join method. This method blocks the main program's execution until the corresponding thread has finished its task. Once both thread1.join and thread2.join are called, the main thread waits for both threads to complete their work before printing the final message. Both threads have finished execution. This example highlights the basic use of threads in Python, showing how you can execute tasks in parallel to increase efficiency and responsiveness, especially for tasks that can run independently. The join method is essential for ensuring proper synchronization, as it prevents the main program from finishing before the threads have completed. This type of parallelism is particularly useful for I/O bound tasks such as file reading, network requests, or tasks that involve waiting or delays, making the program more responsive. 2. Thread synchronization with locks. Question: write a Python program where two threads increment a shared counter 100,000 times each. Use a lock to avoid race conditions. In this example, we demonstrate how to safely modify a shared resource counter in a multi-threaded environment using Python's threading.lock. The counter variable is shared between two threads, each of which attempts to increment it 100,000 times. Without any safeguards, both threads could try to modify the counter at the same time, leading to a race condition, a situation where the outcome depends on the timing of the thread executions. This could result in incorrect and unpredictable values for the counter due to simultaneous access by multiple threads. To prevent race conditions, we use a threading.lock, which ensures that only one thread can modify the counter at any given time. In the increment underscore counter function, the with lock statement locks the shared resource for the thread that is currently executing, preventing the other thread from accessing the counter until the lock is released. This mechanism guarantees that the increments happen sequentially, one thread at a time, preserving the integrity of the shared resource. The thread 1 and thread 2 threads are created to run the increment underscore counter function in parallel, and the start method begins their execution. As both threads run concurrently, they compete for the lock to increment the counter. Thanks to the lock, only one thread can access the counter at a time, ensuring that the increments happen in a controlled manner. After both threads complete their execution, the join method ensures that the main program waits for both threads to finish before proceeding to print the final value of counter. Since both threads increment the counter 100,000 times each, the expected final value of counter is 200,000. By using a lock, we avoid race conditions and ensure that the shared resource is updated correctly. This approach demonstrates how locks can be used to manage shared resources in multi-threaded environments, ensuring data consistency and avoiding errors caused by simultaneous access to shared variables. 3. Producer-consumer problem. Question: write a Python program to implement the producer-consumer problem using QE.Q for three communication between a producer and a consumer thread. In this example, we implement the classic producer-consumer problem using Python's threading and queue modules. The producer and consumer are two separate threads that work concurrently. The producer generates items and places them in a shared thread safe queue, while the consumer retrieves and processes these items from the queue. The goal of this pattern is to manage the flow of data between the producer and consumer in a way that prevents issues like race conditions or data corruption. The producer thread runs the producer function, where it generates items, in this case numbers from 1 to 5, and puts them into the queue using the queue.put method. After each item is produced, there is a simulated delay of 1 second sleep sleep 1 to mimic real world production time. On the other hand, the consumer thread continuously runs the consumer function, where it reads items from the queue using queue.get and processes them. The queue.task underscore done method is called after each item is consumed to indicate that the item has been successfully processed. The loop in the consumer breaks once the last item, number 5, is processed, signaling the end of the consumption. The QQ.Q acts as a thread-safe buffer between the producer and consumer, ensuring that data can be shared between the two threads without the need for complex locking mechanisms. The queue handles synchronization so the producer can safely add items while the consumer simultaneously retrieves them, ensuring smooth and error-free communication between threads. By using the join method on both the producer thread and the queue, the main program waits for both the producer to finish generating items and the consumer to finish processing all of them before continuing. This ensures that the program does not exit prematurely, allowing all tasks to be completed. The final message, producer and consumer have finished, is printed once all items have been produced, consumed, and processed correctly. This example demonstrates a practical use of multi-threading to manage tasks that involve producing and consuming data at different rates. By using a queue, we efficiently handle the flow of data between the producer and consumer, ensuring thread safety and proper synchronization without the risk of race conditions. 4. Thread pool with concurrent.futures.thread executor. Question, write a Python program to demonstrate the use of thread pool executor to compute the squares of a list of numbers in multiple triple threads. In this example, we use Python's thread pool executor from the concurrent.futures module to execute tasks concurrently across multiple threads. The goal is to compute the square of each number in a list using multithreading, which can improve performance by allowing multiple tasks to run simultaneously. This is particularly useful for tasks that are independent of each other, such as calculating squares of different numbers, as it allows the tasks to be divided and distributed across threads. The thread pool executor is initialized with max underscore workers 3, which means that at most 3 threads will be running at the same time. Each thread will pick up a task, which in this case is applying the square function to an element in the numbers list. The executor.map method is used to distribute the work of computing the square across the available threads. This method applies the square function to each element in the numbers list, spreading the computations across the threads efficiently. As the tasks are completed, executor.map collects the results in the same order as the input list, ensuring that the output maintains the correct sequence. The results, which are the squares of the numbers in the list, are returned as an iterator. After the threads finish executing, we use a for loop to iterate through the results and print the computed squares. By using thread pool executor, we simplify the process of managing multiple threads and distributing tasks. This approach allows us to take advantage of parallelism, which can speed up the execution of tasks that are independent and can be processed concurrently. The result is a more efficient and scalable solution, especially for workloads that benefit from multithreading, such as I/O bound operations or simple computations like the one in this example. 5. Deadlock example. Question, write a Python program that demonstrates a deadlock scenario using two locks. In this example, we are simulating a classic deadlock scenario using threading and locks in Python. A deadlock occurs when two or more threads are each waiting for a resource held by the other, leading to a situation where none of the threads can proceed. In this case, we create two locks, lock 1 and lock 2, and two threads that try to acquire these locks in opposite order, which leads to the potential for deadlock. Thread 1 in the thread 1 underscore function first acquires lock 1 and then tries to acquire lock 2. Similarly, thread 2 in the thread 2 underscore function first acquires lock 2 and then attempts to acquire lock 1. Both threads pause for 1 second using time.sleep1 between acquiring the first and second lock, simulating processing time. However, during this sleep, a deadlock situation can arise. If thread 1 acquires lock 1 and waits for lock 2 while thread 2 has already acquired lock 2 and is waiting for lock 1, both threads will be stuck indefinitely, waiting for each other to release their locks. This situation creates a deadlock because neither thread can proceed. Thread 1 is holding lock 1 but needs lock 2 to commit lock, and thread 2 is holding lock 2 but needs lock 1. Since neither thread can release the lock it holds until it acquires the other, they remain stuck, unable to finish their tasks. In this case, both threads will be waiting forever, and the program will hang because the threads can never complete their execution. Deadlock is a common problem in multi-threaded programming where locks are used for synchronization. It occurs when threads are trying to acquire locks in a circular dependency. To avoid deadlocks, developers can use strategies like lock ordering, lock timers, or more advanced synchronization primitives such as semaphores or condition variables. Understanding and managing deadlock scenarios is crucial for writing robust and reliable multi-threaded applications. 6. Thread synchronization with condition. Question: write a Python program where one thread waits for a condition to be met using threading.condition before proceeding. In this example, we are using Python's condition object to manage synchronization between two threads. The condition object allows one thread to wait for a specific condition to be met and another thread to notify or signal that the condition has been satisfied. This is a common threading pattern used when threads need to cooperate and coordinate their execution. The waiting underscore thread function represents a thread that waits for the condition to be met. It uses the condition.wait method, which causes the thread to release the condition's lock and suspend execution until it receives a notification from another thread. When the condition is met, the thread resumes execution, allowing it to proceed with its task. On the other hand, the signaling underscore thread function represents a thread that signals the waiting thread by calling condition.notify. This method wakes up the waiting thread, allowing it to continue its execution. In this example, we create two threads, thread 1 which waits for the condition and thread 2 which signals the condition. Both threads are started concurrently, and once thread 2 signals the condition, thread 1 is allowed to proceed. The join method ensures that the main program waits for both threads to complete before proceeding to the final output. This setup is useful when you want to control the flow of execution between threads, ensuring that one thread only proceeds when a specific event occurs. As signaled by another thread, it provides a simple and effective way to manage dependencies between threads in a multi-threaded application. By using a condition object, you can ensure that threads communicate efficiently and operate in a coordinated manner, preventing race conditions or other synchronization issues. 7. Thread termination using event. Question: write a Python program where a thread can be safely stopped using a threading.event. In this example, we use Python's threading.event to control the execution and termination of a worker thread. The event object acts as a signal that allows the main thread to communicate with the worker thread and instruct it to stop running. This is a clean and efficient way to manage long-running threads or background tasks that need to be terminated in a controlled manner. The worker function is designed to run in a loop, simulating periodic work by printing working and then pausing for 1 second. The loop continues until the stop underscore event is set, which is checked by the stop underscore event dot is underscore set condition. Initially, the stop underscore event is not set, so the loop runs, allowing the worker thread to keep executing. Once the main thread sets the stop underscore event by calling stop underscore event dot set, the condition becomes true and the worker thread breaks out of the loop, printing worker thread stop and terminating. The main thread starts by creating and starting the worker thread. It allows the worker to run for 5 seconds by using time.skip5 to pause execution. After 5 seconds, the stop underscore event.set method is called, signaling the worker thread to stop. Finally, the worker underscore thread dot join ensures that the main thread waits for the worker to fully finish before continuing. This prevents the program from exiting prematurely, ensuring that the worker thread has completed its work and terminated properly. This approach demonstrates a clean way to manage thread termination. Using event, the main thread can signal the worker thread to stop without forcibly killing it, which could lead to resource leaks or inconsistent states. The worker thread gets the chance to gracefully finish its task before shutting down, making this a robust method for managing long-running or background threads in Python. 8. Thread communication using queues. Question: write a Python program where one thread communicates with another using queue.queue. In this example, we demonstrate a classic producer-consumer problem using Python's queue.queue to facilitate communication between two threads, the producer and the consumer. The producer is responsible for generating items and placing them into a thread-safe queue, while the consumer retrieves and processes those items from the queue. This pattern is commonly used in multi-threaded programming to handle tasks where one thread produces data and another consumes data, processes that data. The producer thread runs the producer function, which creates 5 items numbers from 0 to 4. Each item is placed into the queue using queue.put, and the producer pauses for 1 second between each item to simulate time taken to generate the items. The consumer thread, on the other hand, runs the consumer function in an infinite loop, constantly retrieving items from the queue using queue.get. As each item is consumed, the consumer prints the item and signals that the task is complete with q.task_done. The consumer continues retrieving and consuming items until it encounters a none value, which is used as a sentinel to signal that no more items are being produced and that it should stop consuming. After the producer has finished producing all items, the main thread waits for the producer thread to complete by calling producer_thread.join. Once the producer is done, the sentinel none is added to the queue to notify the consumer to stop. The consumer thread will consume any remaining items in the queue, then detect the none value and break out of its loop, signaling the end of its work. Finally, consumer_thread.join ensures that the main program waits for the consumer thread to finish before proceeding to the final message, confirming that both threads have completed their tasks. This design efficiently synchronizes the production and consumption of items between threads using the queue, ensuring thread safety and preventing race conditions. The use of queue.query makes it easy to manage the flow of data between threads without complex synchronization mechanisms like locks. By using a sentinel value none, we can gracefully signal the consumer thread to stop, ensuring clean termination of both the producer and consumer. This pattern is widely applicable in multi-threaded programs where multiple threads need to cooperate and share data in a controlled, synchronous manner. That wraps up our dive into multi-threading in Python. As you've seen, multi-threading can be a powerful tool for improving performance, especially with tasks that involve I/O operations. However, it's important to keep in mind some of the challenges like managing thread safety and working around Python's global interpreter lock-gill. I hope these practical examples have made the concept clearer and given you the confidence to tackle multi-threading questions in your interviews. If you found this helpful, don't forget to like, share, and subscribe for more interview tips and coding tutorials. See you in the next video.